Time is constantly around us, yet it's invisible. It's a concept that goes beyond mere clocks and connects with the very fabric of existence. At its core, time is about the journey from the past towards the future. However, time's nature brings up many fundamental questions. Is it possible for time to have a start and an end, just like everything else does? Can we ever control its steady, one-way flow? Time remains one of the most fascinating and enigmatic elements of our reality. The story of the universe starts with the Big Bang. This event didn't just create matter and space, it was also the moment when time began. This point is where our universe's timeline starts. Talking about time before the Big Bang doesn't make sense with what we currently know in physics. Right after the Big Bang, the universe was extremely chaotic and densely packed. To put it simply, it was like a superhot mix of particles and energy crammed into a very tiny space. During this period, normal physical laws as we know them today didn't apply. It was a time vastly different from what we experience in our current universe. One of the greatest puzzles in cosmology is what exactly happened at the very beginning of the Big Bang. Our scientific knowledge starts just a fraction of a second after this event. In those initial moments, time might have behaved quite differently from what we see now. Right after the Big Bang, in the early universe, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all combined into one. This merging could have greatly affected the nature of space and time. It hints that a single, powerful force might govern the nature of space-time. During this period, something called inflation rapidly expanded the universe. Imagine stretching a rubber sheet incredibly fast. This process might have made time work in ways that we can't observe today. As the universe began to cool, particles formed into the matter as we know it. This shift from a hot, dense state to a cooler, more structured state brought significant changes in how time functions. Gradually, the laws of physics evolved into what we are familiar with today. The four fundamental forces began to separate. This change was key in stabilizing time and shaping it into the form we now understand. Still, the exact nature of time during those initial moments remains a great mystery in modern physics. As atoms formed, followed by stars and galaxies, the nature of time started to look like the linear, predictable flow we know. In our daily lives, we often think of space and time as different things. But in modern physics, they are combined into one concept, space-time. This is a four-dimensional continuum, where space and time are interconnected. This means when we think of a moment in time, we are also thinking of a place in space, and vice versa. Imagine space-time as a vast fabric. This fabric includes the three dimensions of space, length, width, and height, and also the dimension of time. Every event in the universe can be pinpointed using four coordinates, 3 to specify its location in space and a fourth for its moment in time. A point in time is inseparable from a point in space. For instance, to meet someone, you need a specific place, space, and a specific time for the meeting. Understanding this concept is vital to grasping how the universe functions at a fundamental level. Events are not just points in space or moments in time, they are unique combinations of both. This interconnection shapes our understanding of motion, gravity, and the universe's expansion. Understanding spacetime as one concept leads us to Einstein's theory of relativity. This theory explains how objects move not just through space, but through spacetime. It reveals that mass and energy can bend this fabric of spacetime, affecting how time flows and the paths objects take through space. Einstein's theory of general relativity shows that mass and energy can warp the structure of spacetime. We experience this warping as gravity. Large objects, like planets and stars, create significant bends in spacetime. These bends influence how other objects move and how time flows. Another key idea in relativity is time dilation. Time doesn't always pass at the same speed. Both velocity and gravity can change how quickly time passes. For example, time moves slightly slower for someone on Earth's surface compared to someone in space, due to Earth's gravity. This difference is tiny in this case, but it can be much larger in extreme conditions, like near a black hole. A theoretical example of time being stretched is near a black hole. Time slows down dramatically close to a black hole. At the edge, known as the event horizon, time might seem to stop for an outside observer. This extreme slowing of time means that, to someone watching from a safe distance, objects falling into a black hole appear to slow down and nearly freeze as they get closer to it. This is because of the intense gravitational time dilation effect near the black hole. The impact of gravity on time isn't just theoretical, it's something we've actually observed. Take atomic clocks, for instance. These highly accurate clocks show slight time differences based on their position relative to Earth's gravitational field. An atomic clock on Earth's surface, where gravity is stronger, runs a bit slower than a similar clock in a low-gravity orbit. Astronauts experience a kind of time dilation too. For instance, astronauts on the International Space Station, ISS, orbiting Earth at high speeds, are in a weaker gravitational field than people on Earth. Their high velocity also contributes to time dilation. As a result, time passes slightly more slowly for them compared to people on Earth. Another real-life example of time dilation is seen in the Global Positioning System, GPS. The satellites that make up the GPS experience a slightly different flow of time than instruments on Earth. This difference might be small, but it's critical. If we didn't adjust GPS calculations for this using relativity, they would be inaccurate. Relativity is based on the idea that the speed of light in a vacuum is constant and the same for all observers, no matter how they are moving in relation to the light source. This is a key part of Einstein's theory of relativity. The speed of light is about 299,792 kilometers per second. The constant speed of light leads to time dilation. As an object gets closer to the speed of light, time appears to slow down for that object from the perspective of a stationary observer. This isn't just theory, it's been proven experimentally using atomic clocks on high-speed aircraft. The speed of light isn't just the fastest speed at which we can travel. It's also the limit for how quickly information or any effect can travel. This is crucial for understanding the universe's structure. In Einstein's theory of relativity, the speed of light is a constant that links space and time. The speed of light remains constant because it balances the relationship between space and time. We observe time warping at high speeds or in strong gravitational fields because of this balance. When we look at light from an object like a star 100 light-years away, we are actually looking back in time. This is because the light we see now began its journey 100 years ago. So, observing distant objects in space lets us see their past. Imagine if we could teleport instantly 100 light-years away from Earth and look back at our planet. In this hypothetical scenario, we would see Earth as it was 100 years ago. This is because light from Earth, traveling to that point in space, would be showing events from 100 years ago. The fact that light has a finite speed means we can only see parts of the universe where light has had enough time to reach us. This is a key principle in observational astronomy. By looking at distant galaxies and stars, astronomers are actually looking into the universe's history, uncovering cosmic events that happened billions of years ago. Whenever we look at the world around us, we're seeing light that has traveled from objects to our eyes. There's a slight delay even when looking at nearby things, although this delay is very short. This means we're always seeing the very recent past, not the exact present. The light from a book we're reading or a tree we're looking at took a tiny bit of time to reach our eyes. This insight changes how we understand the present. What we often consider as the present moment is actually a past event by the time we become aware of it. The concept of a true present is visually elusive. As soon as light reaches us and we process it, that moment has already become the past. This effect is more dramatic with astronomical distances. The stars we see at night are images from the past. Some may not even exist in their current observed state anymore. One of the biggest challenges in physics is reconciling quantum mechanics with Einstein's theory of relativity. They seem like two different sets of rules for the universe. Relativity suggests that time can stretch and compress, but quantum mechanics views time as a constant. Figuring out how to combine these two perspectives is a major scientific goal. In the quantum world, particles like electrons or photons can exist in various states and even multiple states at once, known as quantum superposition. However, time doesn't have a quantum state. Unlike a particle, time can't exist in two states simultaneously. In quantum mechanics, time is like a consistently ticking clock that oversees the changes in quantum systems but doesn't affect them. In the equations physicists use for quantum systems, time is just a variable that tracks how the system changes. Unlike other variables, time doesn't represent a characteristic of the quantum system itself. It's more like a progress indicator, similar to page numbers in a book. They show you where you are but aren't part of the story itself. In the quantum world, time dilation doesn't happen. It doesn't matter how fast particles move or how much energy they have, time progresses at the same rate. One of the biggest tasks in modern theoretical physics is creating a theory of quantum gravity that describes gravity at the quantum level. In such a theory, physicists would expect to treat time and space as quantum entities, possibly with their own quantum states. This would be a significant shift from how time is currently viewed in quantum mechanics and could fundamentally alter our understanding of time. While quantum mechanics sees time as constant and unchanging, thermodynamics introduces the concept of time's variability and irreversibility. This difference underscores the complex nature of time in various areas of physics. Entropy is a term in physics that usually refers to the level of disorder or randomness in a system. In simple terms, it measures how spread out or mixed up things are. A system with high entropy is very disordered, while one with low entropy is more ordered. According to the second law of thermodynamics, in an isolated system, the total entropy, or disorder, tends to increase over time. This law is a key principle in thermodynamics. Imagine a billiard table with balls neatly arranged. This setup represents low entropy, it's very orderly. When you hit the balls with the cue, they scatter randomly across the table. This scattering increases entropy because the balls are now more disordered. If we try to put the balls back into the original pattern, we can do it, but it requires external effort. We have to manually move the balls, adding energy and interference to the system. However, this action doesn't really reverse entropy. While it might make the billiard table more orderly, it increases entropy elsewhere, like the energy used to move the balls. This example helps explain the arrow of time. Even if we recreate a past state, we don't reverse time or reduce the overall entropy of the universe. Time and the universe's total entropy keep moving forward, despite temporary local decreases in entropy. The increase in entropy leads to the effect known as the arrow of time, giving a direction from past to future. This is why we can remember the past but not the future. It's also why certain processes, like a hot cup of coffee cooling down or smoke spreading in the air, only happen in one direction. Considering massive objects like planets and stars can warp space-time significantly, it's hypothesized that time travel might be possible. One of the most discussed ideas in general relativity is wormholes. These are hypothetical tunnels in space-time connecting two distant places or different times. If we could create and stabilize wormholes, they might allow travel to different times. Another theoretical idea from relativity is the closed time-like curve, CTC. In some solutions to Einstein's equations, these curves loop back on themselves, theoretically creating a path in space-time that returns to its starting point in time. However, whether such structures are physically possible is still a topic of debate among physicists. In many science fiction stories, time travel is shown as just moving back or forward in time at the same place on Earth. For example, a character steps into a time machine in 2023, presses a button, and appears in the same place in 1923. This idea simplifies time travel by overlooking the fact that Earth, our solar system, and our galaxy are always moving. Actually, space and time are intertwined in what's called the space-time continuum. If time travel through wormholes is possible, it would have to account for both space and time. This is because Earth's position in space changes over time due to its orbit around the Sun, and the solar system itself is moving through the Milky Way. Accurately arriving at a specific time and place can be extremely complex. To travel back a year, for instance, one would need to calculate Earth's exact location in its orbit at that time, considering the Sun's movement through the galaxy and the galaxy's movement through space. If wormholes could be used for time travel, they'd have to link not just 2 points in time but also 2 points in space. This means calculating the changing positions of celestial bodies to ensure arriving not just at the right time, but at the right place in space. Imagine someone travels through a wormhole to a future date. From their perspective, they skip the in-between time and instantly arrive in the future. But for someone staying in the original time, time moves normally. For the wormhole traveler, their experience of time is different. They jump from one point to another. For them, the future they reach becomes their new present. For someone not traveling through the wormhole, time flows normally, and they reach the future date the traveler arrived at, experiencing every moment in between. In both scenarios, the arrow of time and the progression of entropy continue forward. Even though the traveler skips a portion of time, they don't change the direction of time's flow or the increase in entropy. They've simply moved to a different point on their timeline. Whether this counts as real time travel depends on how you define time travel. The traveler moves to a future stage without experiencing the intervening period. They travel through time in a non-traditional sense, bypassing the regular sequence of moments. This thought experiment highlights the relativity of time, how it's experienced differently based on one's position and movement. It shows that while traveling to the future is theoretically possible, it's experienced differently by travelers and observers in actual time frames. In theoretical models that consider time travel with wormholes, traveling to the future seems possible. But returning to the past, to the traveler's original time frame, poses greater challenges. Most of today's scientific theories, including general relativity, don't offer a way to travel back in time after moving forward. Current physics also doesn't support the idea of communicating from the present to the future or the other way around. While time dilation allows for different rates of time passage, it doesn't enable direct communication across different times. The second law of thermodynamics adds to the difficulty of going back in time to alter future events. For a wormhole to work for time travel, it needs to be both navigable and stable. Theoretically, if one end of a wormhole experiences more time dilation than the other, either by moving it at high speeds or placing it in a strong gravitational field, the two ends could be in different times. However, stabilizing a wormhole would likely require exotic matter with negative energy density, which remains hypothetical and undiscovered. The twin paradox is a thought experiment in physics. Imagine twins, where one travels into space at near light speeds, the traveler, and the other stays on Earth, the stay-at-home. Due to time dilation in special relativity, time would pass differently for the traveler. As the traveler moves at a significant fraction of the speed of light, time on Earth appears to slow down for them. When they return, the stay-at-home twin has aged more than the traveler. Although they were the same age when the journey began, now the stay-at-home twin is older. This paradox arises because the laws of physics are the same for all observers in uniform motion. The traveler sees themselves as stationary and Earth as moving. So, why doesn't time dilation affect the stay-at-home twin similarly? The answer lies in the traveler's change in velocity as they turn to return to Earth. This change breaks the symmetry of the situation. The stay-at-home twin remains in a consistent inertial frame, without acceleration, so they don't experience the same dilation effects. The twin paradox isn't really a paradox but rather a demonstration of the principles of special relativity. It shows how time is relative, not absolute, and can differ for observers moving at different velocities. The grandfather paradox is a well-known thought experiment in time travel. It describes a fictional scenario where someone travels back in time and does something to prevent their own existence. For example, imagine a time traveler going back and inadvertently causing their grandfather's death. If this prevents their grandparents from meeting, their parent won't be born, and neither will the time traveler. But if the time traveler never existed, how could they go back in time to prevent their grandparents from meeting? This creates a logical loop or paradox. Several theories have been proposed to resolve this paradox. Some suggest that changing the past results in a new timeline or universe. In this case, the time traveler's actions would create a parallel universe where they don't exist, but their original timeline remains unchanged. The Novikov self-consistency principle, proposed by physicist Igor Dmitrievich Novikov, argues that if time travel were possible, events would naturally prevent inconsistencies. Essentially, the laws of physics would stop the time traveler from taking actions that create a paradox. One of the most intriguing theories in quantum mechanics is the many-worlds interpretation, proposed by Hugh Everett III. This theory posits that all possible outcomes of quantum events occur in separate, parallel universes. Regarding the grandfather paradox and time travel, this interpretation suggests that if a time traveler changes something, they don't alter their original timeline. Instead, they create or enter an alternate universe where the consequences of their actions are different. The concept of alternate timelines suggests that each decision or event leads to a new branch in the universe, with every possible outcome creating a new timeline. These alternate timelines represent different histories and potentially different versions of ourselves and the world. In quantum mechanics, every event in a quantum state could result in different branches of the universe, implying the existence of an infinite number of parallel universes, each with a different sequence of events or choices. While the many-worlds interpretation and the multiverse concept are fascinating, they are also controversial. One major criticism is the lack of empirical evidence and the difficulty in experimentally testing these theories. One popular scenario for the universe's end is the heat death, or the Big Freeze. Based on the second law of thermodynamics, which says entropy, or disorder, increases over time, this theory suggests the universe will keep expanding. As it expands, energy will spread out and become evenly distributed. This leads to a state of maximum entropy, where no more activity can occur, resulting in a cold, lifeless universe. Another theory is the Big Crunch, where the universe's expansion eventually stops and reverses, collapsing back into a singular state. This would be like the Big Bang in reverse, with all matter and space-time condensed into a single point of infinite density. In this scenario, the traditional flow of time as we know it might cease. The Big Rip theory proposes that the universe's expansion will accelerate so much that it will eventually tear itself apart. If the expansion rate surpasses all other forces, galaxies, stars, planets, and even atoms would be ripped apart, leading to a universe where traditional concepts of time are irrelevant. Some quantum theories predict even more unusual endings. For example, quantum fluctuations could trigger a sudden shift, creating a new universe with different physical laws where our understanding of time is no longer valid. These scenarios also pose philosophical and existential questions. What does it mean for time to run out? Is it the end of changes and events, or the end of the universe as we know it? From both philosophical and physical perspectives, time is a fundamental aspect of our universe. Philosophically, the end of time might mean a state beyond our current existence, challenging our traditional ideas of cause and effect. Physically, events like the heat death, Big Crunch, or Big Rip suggest a universe where traditional physics don't apply. Quantum cosmology and string theory even consider cyclical universes, where universes are reborn under different physical laws. These theories, when viewed through metaphysical, theological, and scientific lenses, highlight the limits of our understanding.